Hello, welcome to another module in this massive open online course. So in the previous module we have looked at the bandwidth of an FM signal, the approximate bandwidth occupied by an FM signal, which is given by the Carson's rule. Okay. So in this module let us start looking at the demodulation of an FM signal. So we want to start looking at basically want to start looking at FM signal demodulation, that is the demodulation of an FM, that is the demodulation of an FM signal. And FM signal can be demodulated. The technique for demodulating an FM signal is through the use of a differentiator circuit. Okay, so we are going to illustrate how to demodulate the FM signal using a differentiator. So FM signal can be demodulated. This can be demodulated using a differentiator. The idea is basically we have this FM signal. Okay, so I have an FM signal S of t. I can give it as input to a differentiator circuit which performs the operation which differentiates the input, and the output is d by dt of st. This is your differentiator. This is your differentiator circuit. By the way, a differentiator you can realize you will realize is a linear time invariant system. Okay, so this is a very important property of the differentiator, correct. So this is a linear time invariant system. Okay, so you can also note that the differentiator is an LTI system. Okay. And now let us consider our FM signal, our standard FM signal, which is given as ST equals AC cosine 2 pi FCT plus 2 pi KF integral 0 to T m tau d tau. Okay, this is my FM signal. Okay, we have seen this several times before. This is an example of a canonical or a general. This is an example of a general FM signal. Now, if we pass this through a differentiator, now when we pass this through a differentiator. So, when we pass this through a differentiator circuit, the output is, well, we have seen that it differentiates the input, that is dSt by dt, that is the derivative of St, which is AC cosine, the signal is AC cosine 2 pi FCT plus 2 pi KF integral m tau d tau. You can see the derivative of this is minus AC, derivative of cosine is minus sine. So, minus sine 2 pi FCT plus 2 pi k f integral m tau d tau times the derivative of, well, the argument, that is 2 pi f c tau plus 2 pi integral 0 to t m tau d tau, that is the argument of the cosine function. Okay. So, we are employing the chain rule for differentiation, which is basically equals minus a c, well, sine 2 pi f c t plus 2 pi integral 0 to t m tau d tau times, now you can see the derivative of 2 pi f c t plus 2 pi k f integral 0 to t m tau d tau is nothing but 2 pi f c plus derivative of 2 pi k f integral 0 to t m tau d tau is nothing but 2 pi k f m t, okay, where we use the property, the derivative, we are using the property that the derivative with respect to t of integral 0 to t m tau d tau is nothing but m t. Okay. This is the property that we are basically using. Okay. It is a very simple property that if you differentiate the integral of a function, you get the function itself. Okay. And therefore, now I can rewrite this as minus a c, bringing the argument to the front, 2 pi f c plus 2 pi k f m t times, well, sine of 2 pi f c t plus 2 pi k f integral 0 to t m tau d tau. And now, if you look at this signal, the resultant signal. So, this is basically your output of the differentiator, correct. That is, this is basically your dst by dt. And now, if you can see, look at the output of this differentiator, you can see that the envelope of this is basically envelope of the output is a sinusoidal signal, the envelope, the output is basically the envelope of output of differentiator equals AC 2 pi f c plus 2 pi k f m t. So, what you can see is that the envelope of the output of this differentiator is proportional to m t. Okay. And therefore, we pass this, the output of the differentiator, to an envelope detector. Okay. So, pass this through an envelope detector, we have already seen the envelope detector. So, pass output of differentiator through envelope detector. So, pass output of differentiator through the output of differentiator through an envelope detector, correct. and the resultant output is, and the net output is, that will give us the envelope which is basically AC 2 pi FC plus well 2 pi kf mt, which is basically, now consolidating the terms, this is basically AC into 2 pi, correct, FC plus kf mt, and which is equal to basically, now if you can look at this, which is equal to 2 pi AC FC into 1 plus kf mt divided by FC. Okay. And now we know, correct. So, now we have the output of the envelope detector, this is given by, this is your output of the envelope detector which can be used to recover. So, this is the output of the envelope detector, and this can be used to recover the original message signal MT. This can be used to recover the original message signal MT. So, this is the output of the envelope detector which can be used to recover the original message signal MT. However, remember, for no phase reversals, all right, we need a condition, correct, that is the amplitude model. Remember, when we looked at an amplitude modulated signal for envelope detection, the condition for no phase reversal is that the signal should not be over modulated, correct, which means, that is, if you can look at this quantity here, signal should not be over modulated, which means for envelope detection, recall that the signal should not be, for envelope detection, recall the signal should not be over modulated. Okay, since over modulation results in phase reversals not arising from the carrier. Remember, since over modulation not arising from the carrier, and the condition for, and now if you look at this signal, 2 pi AC times FC plus kf mt. Now, if you look at this signal, okay, the condition for no envelope distortion is that this has to be greater than 0, which implies basically FC has to be greater than or equal to Kf times maximum of magnitude MT. Okay. So, basically your Kf has to be greater than or equal to maximum of magnitude of. So, this is the condition that we require, remember this is the condition that we require for no envelope distortion, that is Fc, the carrier frequency, has to be greater or equal to Kf times maximum magnitude mt, that is the maximum of the magnitude of the message signal. And now if you look at our frequency, correct, now let us go back to our frequency. The frequency, the instantaneous frequency Fit is basically, if you look at that, that is basically your, well, the phase, let us look at the phase 2 pi, well, Fct plus 2 pi Kf integral 0 to t m tau d tau. Now, the instantaneous frequency is 1 over 2 pi derivative of the phase, which is equal to, well, 2 pi Fc plus 2 pi Kf mt, which is equal to again 2 pi Fc 2 pi Fc plus 2 pi Kf 2 pi Kf I am sorry, Fc plus Kf mt, because there is a factor of 1 over 2 pi. So, this is simply Fc plus Kf times mt, and therefore, the frequency deviation, if you remember our frequency deviation delta f equals maximum of magnitude Fit minus Fc. This is how we derived the frequency deviation, which is maximum of magnitude mt, which is Kf times maximum of magnitude So, our delta f, our frequency deviation delta f is nothing but Kf times maximum of the magnitude of mt. And now, if you look at this, you will realize that this quantity Kf times maximum of magnitude mt is nothing but delta f. Therefore, the condition for no envelope distortion, what it reduces to basically the fact that the frequency, carrier frequency must be greater than the maximum, the peak frequency deviation of the FM signal. Therefore, condition for no envelope distortion. Very interestingly, the condition for no envelope distortion is basically Fc greater than delta f. Okay. So, Fc, so if remember this is your maximum frequency deviation. Okay. Let me also mention that this is your maximum frequency deviation and this is your carrier frequency. This is the maximum frequency deviation and this is the carrier frequency, and the condition for no envelope distortion is that Fc is greater than or equal to delta f. And therefore, if this condition is satisfied, that is the carrier frequency of the FM signal is greater than the maximum frequency deviation, there will be no envelope distortion. However, you can see that this is naturally true for an FM signal, since the carrier frequency is a very high quantity compared to the frequency deviation. For instance, let us take a typical example. Okay, let us take a typical example of an FM signal. Okay. You can see the carrier frequency Fc equals Well, for FM signal the carrier frequencies are typically in the range of 100 megahertz. These are the FM carrier frequency, okay, 90 megahertz to about 105, 110 megahertz, okay. FM carrier frequencies approximately, or they are of the order of basically 100 megahertz, and the bandwidth or the maximum message frequency you can say FM, right, FM is approximately of order of let us say 10 kilohertz. You can say this is the bandwidth or the maximum message frequency, okay. This is the bandwidth or maximum message frequency, and therefore now if we have a modulation index beta equals 10, let us say this is our modulation index, and we know that delta beta is basically delta f divided by Fm, the maximum frequency component, which implies Fm, which implies delta f, which implies the frequency deviation delta f is beta times Fm, which is 10 times, well, our bandwidth is well, it is 10 times 10 kilohertz, which is equal to 100 kilohertz, which is equal to 0.1 megahertz. So, your delta f is approximately 0.1 megahertz. Your carrier frequency Fc is basically of the order of 100 megahertz. So, you can clearly see that delta f is much smaller than Fc. This is approximately 0.1 megahertz, this is approximately 100, this is approximately 100 megahertz, okay, Fc. So, this is your delta f, this is Fc. So, Fc is approximately 100 megahertz, your delta f is approximately 0.1 megahertz. So, what you can see is that this delta f, this quantity delta f is typically, that is a frequency deviation, is typically much smaller than Fc, the carrier frequency for a frequency modulated signal, okay. So, this quantity, since the frequency deviation is much less than carrier frequency, tracing back our steps, it means that basically there is going to be no envelope distortion, alright. There is going to be no envelope distortion because the envelope, this quantity Fc plus Kf times Mt is always positive, therefore, there is going to be no envelope distortion, and that in turn means that differentiation followed by envelope detection can be used for can be used as one of the techniques for demodulation of an FM signal, okay, and which is rather simple because it is a low complexity technique which requires a differentiator followed by a envelope detector. Again, as we have seen, envelope detector is a simple circuit that can be implemented with relatively low complexity. So, we will stop this module here and look at other aspects in the subsequent modules. Thank you.